Okay, any questions before we get started? All right. Well, so this is the sort of last day of class. I mean, we're supposed to get together for finals week, which is Tuesday, which is the first day that I'm allowed to come back to campus in theory. Let me just say, I'll let you know the status of what's going to happen Tuesday as it progresses. Obviously, there's no final, but should we get together, I'll let you know. The default will be yes, and I will do it in our classroom, but I'll update if anything changes. Any questions on the homework or anything? You got your last homework due today. If you need more time, just let me know, because I've made up the due date of Friday, but it's, if you get it to me reasonably quickly, I can get things graded. And let's see, yeah, all your homeworks are graded up through 10 except for 9, and I'll grade 9 and 11 and have that back to you pretty quickly, I hope. Okay, I loathe doing this, but I'm going to do it anyway because I can't write on this thing. I might do a little bit of writing, but I'm gonna go back and forth, like kind of with the notes. There we go. So here are some things I wanted to talk about. We did a bunch of examples of valuation domains last time, and I want to talk about. I've just got it listed as an exercise here, but I want to talk about the veracity of this theorem because it's really freaking important. If R is an integral domain with quotient field K, and R bar is its integral closure, then R bar is equal to the intersection of all valuation overrings of R. So let's see how we might do this. The first thing I need to, let's see, I might need to. The first thing I want to do is I want to point out this kind of intermediate lemma here. First lemma that I would use in proving this is the following. The integral closure of R is integrally closed. So in other words, the integral closure is a closure operation. So when you start with R and you look at its integral closure, well, it's natural to ask now, okay, is this new ring R bar integral closed? The answer is yes. So it's actually a closure operation in that sense. This is not true. Let me point out this example. This is not true for complete integral closure. There is a very famous example by Gilmer and Heinzer, which actually Todd Fenstermacher has generalized in his thesis. Let me give you the following example. Look at, let F be a field, and I'm not going to go through all the details because there's some details to be shown here, but I want to take clear F be a field and consider ring R F with X to the N. Whoops, and I'm going to have to adjust this. Y to the N times let's see. Oh, actually, I think it's this way. Yeah. So just to give you an idea how this spreads out, just so in particular, you have x in here, right? Because when here we're going to take n to be greater than or equal to 0. So you get x to the 1 times y to the 0. Then the next term you get, the next monomial you get is x x to the 3, y to the 3. And then you get x to the 5, y to the 10, and so forth and so on, right? Now, if you look at the complete integral closure of this, so I'm gonna let prime denote complete integral closure. Notice that, right, notice that x and y are in the quotient field of R. So I want to make sure that I'm playing in the right playground. And notice that why is this the case? Because notice that x is certainly in the quotient field because x is in fact in R itself, right? And so since x is in the quotient field, then y cubed is in the quotient field because you can just divide x cubed y cubed by x cubed. So now you got y cubed in the quotient field. And now you can divide the next term by x to the 5th, and you get y to the 10th is in the quotient field. And so now you get y's in the quotient field because you got y cubed and y 10th, so you got y in the quotient field. Also note that that x to the x to the 2n plus 1 times y to the 2n plus 1 to the n. Right. Right. Is in R. Let's see, I seem to be off by a little bit here. Oh, right. That comes later. Notice that x and y are in the quotient field of R. And the first thing I want to notice is x to the 2n plus 1. Whoops. Y to the n times 2n plus 1 is equal to x, y to the n. All to the 2n plus 1. So x, y to the n is in the So xy to the n is in the complete integral closure of R, right? And I put complete in parentheses because actually xy to the n is actually integral, right? Because there's a large power of it that's actually in R, right? And so it's actually xy to the n is a root of t to the 2n plus 1 minus xy to the n to the 2n plus 1. So there you go. So actually, it turns out you can show that the integral closure of R is equal to f xy to the n, which equals f x xy xy squared, etc. And so what this means is, so R prime is not completely integrally closed. Now, for me to make this statement really on solid footing, you have to show somehow that y is not almost integral over the original ring, and that's a bit of a computational pain, but you can do it. And so actually the integral closure is actually integrally closed, is now completely integrally closed. This is f xy. Because you have that y is almost integral. And actually, I know this last one is in fact completely integrally closed because fxy is a UFD, and UFDs are always completely integrally closed. So the upshot is integrality is better than almost integrality in that respect. Integrality is a closed operation, but it's not. So let's let t be, let's prove the lemma. Let t be the integral closure of R, and let z be integral over t. Well, that means that z to the n plus t sub n minus 1 t, or z to the n minus 1 plus t sub 1 z plus t sub 0 is 0. That's of course what it means to be integral, where each t sub I is nt. Now, what that means is each ti is integral over R. So for each t sub I, or for each t sub I, there is a finitely generated R module A sub I, such that t sub I, A sub I is contained in A sub I. Remember, that was one of our equivalent, excuse me, one of our equivalent bits about integrality, right? So what do I want to do? Let me make a big fat finitely generated R module that will work. So we now consider generated by well, actually, let me first do, let A be the finitely generated R module A sub 0, a sub 1, a sub 2, dot, 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 all the way up to a sub n minus 1, right? So what I'm doing is I'm smashing all these modules that suck in these coefficients, right? A0 sucks in T0, A1 sucks in T1, and so forth and so on, right? Okay, so far? And this is equal to A. Now what I want to do is consider, and this is finitely generated because even though this may be big, the generators are all possible products of the generators of A0, A1, A2, etc. So now consider the R module, the finitely generated R module I guess I need A, comma, ZA, Z squared, A, comma, dot, 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 comma, Z, n minus 1. Again, this is finitely generated, right? I mean, if A has k generators, and this thing has n minus 1 times k generators. So we got a lot of generators here, folks, but it's still finitely generated, right? And notice that Z, let me call this module something so I can be lazy. We'll call this module B. Notice that ZB is contained in B. And the reason is, certainly if you have something in A, then ZA is contained in the next step, ZA. If you have something in ZA, it's contained, and so forth. And if you have something in Z to the n minus 1A, when you multiply that by Z, then you can redistribute the Z to the n you now have using the equation of integrality and replacing it with the lower powers, and they get all sucked in as well, right? Everybody okay with that? So now we've got the lemma we want. That is to say, we now know that the integral closure is integrally closed, right? So let's get on to the proof of the theorem. Proof biggie, can't you see? So what we want to do first is show that R is well, let T be the integral closure of R. We show that T is contained in every valuation overing of R. And that'll be one of the containments. So now that I've got this lemma, this is the simpler of the containments. So note that R is contained in V because by assumption, we're looking at the valuation overrings of R. So these are, since it's an overring of R, it has to contain R. Now apply integral closure. This means T is contained in the integral closure of V where this unfortunate notation means the integral closure of V. But by the previous lemma, we know that the integral closure, if the ring's integrally closed, then the integral closure is itself. And we already know that valuation domains are integrally closed. We proved that. So there's one containment. The integral closure is contained in the intersection of the valuation over rings because, you know, they're all integrally closed. Now, the interesting part is the other direction. So we need to show, we now need to show that if, say, omega is in every valuation overing, then omega is integral over R. All right, so this is really the interesting part of it. So recall that omega is integral over R if and only if omega is in R y'all remember that one?
Yes.
Okay, good. That's helpful then. So suppose that omega is not integral over R, then omega is not in correct? So in R joined with the ideal is a proper ideal. Correct? But we know that there is a valuation overing of R and hence of R. So if it's an overring of R adjoined with omega inverse, it's a valuation overring of R as well, such that omega, the ideal omega inverse survives. Let's call this valuation overing A. There's a valuation overing A of R such that this ideal survives in A, correct? So omega is not in A, because if it were, then the ideal omega inverse wouldn't survive because it would be the whole thing. And this is our desired contradiction. Okay, now tell me that's not cool. Any questions on that?
I've got a quick question on the last step. What's omega not being in A contradicting exactly?
Omega, because remember, omega is if you look at the first line here, omega's in every valuation over ring of R.
Oh, okay, got it. Okay, yeah.
Okay, any others? Okay, so let's get back to this here. So now we've totally defeated that theorem. I wanted to talk a little bit about, and we'll continue this on Tuesday if everything works out. So I want to talk about invertible ideals. How many of you have ever heard of how many of you have heard of invertible ideals before? Anybody ever heard of that? No? Or have you ever heard of Dedekind domains? Dedekind domains, I mean, some of this came out around the time of like Fermat's last theorem, close to that. Fermat's last theorem would have been proven in 1847, I believe it was, if it were the case that every ring of algebraic integers had unique factorization into elements. And a proof was given, assuming that, but it turned out that these cyclotomic rings of integers, they have unique factorization for a while, but then after a while, a lot of them crop up and do not have unique factorization, so the proof wasn't any good. Dedekind domains is turned into a rich field of study, and it was one of the sort of fixes to this. So here's the deal. The best thing in the world is a PID, and second best thing is a UFD. Now, what happens in a UFD? In a UFD, every non-zero non-unit factors uniquely into prime elements, right? Let me restate that from another point of view. In a UFD, every principal ideal, every proper principal non-zero ideal factors uniquely into principal prime ideals, right? You can do it that way. Dedekind domains take the unique factorization into the realm of ideals, right? So it may not be the case that all your elements factor uniquely into primes, but in a Dedekind domain, what happens is all your non-zero proper ideals factor uniquely into prime ideals. Now, here is and there are large examples of this. The integers have this property. In fact, any principal ideal domain has this property. UFDs in general do not have this property. If they're bigger than PIDs, that is, if they're more than one dimensional. So if they have like non-zero ideals, non-zero prime ideals that aren't maximal, you don't have this property. But if you're a number theory addict, any ring of integers that you've seen, z adjoined with the square root of -5, the Gaussian integers, z adjoined with the square root of 89, these 89, yeah, that's cool. 3 mod 4, good. These are all Dedekind domains. So we need to start with a couple of definitions here. Let R be a domain with quotient field K. We say that an R submodule of K is a fractional ideal if there is a non-zero R in R such that R times I is down inside of R. Okay, so a fractional ideal, what does this condition mean? It means that basically everything in I has a common denominator, right? Because there's a fixed R that allows you to blast everything back into the original ring. So let me give you an example here, an example and sort of a non-example. So here are some fractional ideals. That is every 1/2 of every integer. So this is just the set like 0, 1/2, 1, 1.5, 2, 2.5, 3, and so forth, and all the negatives as well. This is a fractional ideal because notice that 2 times this module is in Z. 2/3 of Z are fractional ideals of Z. Q is not a fractional ideal, because there's no single R that's going to knock every rational number back into the integers, because there's, I mean, basically there's too many primes, right? So these are the fractional ideals. Which shows better at this. And this is a finiteness condition. So notice, let me also point out that if you look at the definition, if I is any ordinary ideal, so it's an ideal that's contained in R, then that's a fractional ideal automatically, because you can just take little r to be 1 because it's already in there, right? So fractional ideals generalize ordinary ideals in a certain sense, but they're R modules. Let I be a fractional ideal. We let I inverse be all the stuff in the quotient field that blasts I back into, oh, that's a typo, isn't it? Blasts I back into I. So let me correct that. Yeah, so that's a typo in the notes. Let me, can't believe I'm still getting ones that bad. So notice that I inverse is the set of all X in the quotient field such that Xi is contained in R. Right. Notice that I inverse is contained in R. Right, just by definition, when you multiply anything in I times anything times I inverse, you're in R. If I inverse equals R, we say that I is invertible. So how about some examples? Well, let me point out that if R is any ring, a domain. So I'm always going to be talking about domains here. R is a domain, and 0 is not, and let's write X equals A over B with A, B in R. Okay, so if R is a domain and X is a non-zero element of K, the quotient field, so we'll write X as A over B, where AB is an R, then XR is a fractional ideal. Notice that B times XR is contained in R, because B times X is equal to A, and A is in R, right? And it's fairly easy to see that XR inverse is equal to X inverse R. And that XR X inverse R is equal to R. So in other words, any principal fractional ideal that is generated by a single element of the quotient field always is invertible, right? Because X times X inverse is 1. And so what's the point of all this business with invertible ideals? Well, here's one of the big deals about this. If I and J are invertible ideals, then so is IJ. So the invertible ideals of R form a group. Well, let me be more specific, an abelian group under multiplication. Anybody want to tell me what the identity is?
I'm gonna guess R.
It is R. Right, because R times any ideal is just that ideal back, because these are all R modules. Let me point out that, and so you can probably, you've got the, I'm not going to go through the details of this because I think you've got the tools to do this computation. But let me point out that to say that an ideal is invertible is actually a very strong condition. And obviously all principal ideals, all non-zero principal ideals are invertible. But ones that aren't invertible are a little bit harder to find. Let me give you an example or two. Let F be a field and look at this ideal here. Let R be a polynomial ring over F of 2 variables. Let I equal now this is an ordinary ideal, so it's a fractional ideal. It's already inside the ring. See if you can compute this. It turns out that I inverse in this case is just equal to R itself. And actually you can use kind of a degree argument to show this. So in this case, I inverse equals I, which is strictly contained in R. So this I is not invertible. Let me give you another example. Let R equal let R be Z adjoined with the square root of -5. Okay. And consider the ideal, again, an ordinary ideal. Consider the ideal generated by 2 and 1 plus the square root of -5, right? Notice that this is an ideal inside R. I first claim that this is proper. And how am I going to do that? Well, you can just get on your horse and ride, right? So suppose, if not, I can write 1 is equal to 2 times a plus b square root -5 plus 1 plus square root -5 times x plus y square root -5. And I challenge you all to multiply this out and equate some coefficients. And I think you'll get a contradiction if you reduce things mod 2, right? There's a parity thing going on and it just can't be done. All right, so I'll leave that now. Also, this ideal I is not principal. Let me kind of argue that a little bit. Do y'all remember when we talked about norms of elements like this? Notice that the norm of 2 is 2 squared, which is 4. And the norm of 1 plus square root of -5 is multiply that by its conjugate, 1 minus square root of -5, and you get 6. So your generators have norm 4 and 6. And so if there is a principal generator of this, it has to have norm 2, right? Norm 1 means that it's a unit, and if you believe that it's proper ideal, it can't contain a unit. So this would have to have an element of norm 2 to divide both of these. And you can check that the square root of any, or you can check that the norm of any element of the form x plus y square root -5 is x squared plus 5y squared. And it's impossible to represent 2 as a square plus 5 times another square. So this ideal is not principal either. But notice, let me do this. This is crazy stuff. If you look at I squared, right, it is generated by 4, right? So it's generated by all the products of the generators, right? So it's generated by 4 and 2 times 1 plus square root -5. And then the product, and then the square of 1 plus square root -5, which I guess is -4 plus 2 square root -5. Is everybody cool with that? Did y'all see where I got all that stuff? And I claim that this is the ideal generated by 2, right? Now, it should be clear, I think, that 2 divides every one of those generators, right? It divides the first one, and it divides the second one, divides the third one in that, right? So to show equality, all I have to do is show that the left-hand side actually contains the number 2, and then I'll have equality. Because that would mean that since 2 contains the left-hand side, if the left-hand side contains 2, we've got equality. Everybody okay with that? Now, if you subtract, so it suffices, show that 2 is an element of I squared. And to this end, notice that 2 plus 2 / square root -5, I guess minus 4 plus 2 square root -5 is equal to 6. So because of those last 2 generators, I've got a 6 in there, and I've got a 4, and 6 minus 4 is 2. And so I've got it. So These two are the same. Now, this should probably strike you as very strange because generally speaking, when you take powers of ideals, they tend to need more generators, right? I mean, if you look at this ideal that I had up here that's not invertible, the ideal generated by xy in fxy, if I square that ideal, I actually need 3 generators. And then I need 4 if I take the cube of it and so forth and so on, right? You tend to need more and more generators. This is rather surprising because what we have is we have an ideal that's squared and it's a principal ideal. And that also proves it's invertible because notice that I times I is equal to the ideal generated by 2. So 1/2 I times I equals R. And so the inverse of I in this case is 1/2 I. Any questions on that? Let me give you, so I think I've just got time to do it. I'll give you one more theorem. And this I think is not so obvious, but it's a really cool theorem. If I is invertible, then I is finitely generated. Let me point out, of course, the converse is not true. We have given a couple of examples of finitely generated ideals which are not invertible. But if it is invertible, it's finitely generated. And I think I can probably prove that fairly quickly. Suppose I is invertible. And J is its inverse. So this saves me from writing exponents all the time. So IJ equals R, right? Because that's what it means for ideal to be invertible. So there are A sub 1, A sub 2, dot, dot, A sub n in I and B sub 1, B sub 2, dot, dot, B sub n in J, such that A sub 1, B sub 1 plus A sub 2, B sub 2 plus A sub n, B sub n equals 1. Everybody okay so far? So I claim that I is generated by A sub 1, A sub 2, A sub n. Notice that certainly this ideal is contained in I, right? Because the generators are all in there. Let X be in I, then using the above equation, and in fact, I'll sort of dramatically do it here. Yeah, I'll do it like this. Using this equation here, multiply this sucker by X, and I'll put X in like strategic places here. XBN. XB2. XB1. Right? Notice that since X is in I, each XB sub I is in R, right? Because X is in I and the BIs are in the inverse of I. That means that X times any BI blasts you back into R. So X is an R linear combination of the A sub I's. And there you go. So it's finitely generated. Any questions on that? Any questions? Okay, folks, I will let you know about Tuesday update. I mean, my default is sort of I'll be there and give kind of a last lecture thing, but I'll let you know if anything comes up. And listen, my rule is once my student, always my student. If I can be of any help to any of you in the future, let me know. Be sure to do the evaluations too, because everybody gets an extra 100 on the homework if you do that, if you get 90%. So be sure and do that. Other than that, any questions? All right, you all take it easy and we'll, oh, Jeff, did you have one?
Yeah, are you gonna do office hours on Zoom right now, or what's the
Well,
plan?
I mean, you don't want my cooties. Yeah, yes, I am going to be doing office hours and I got no choice but to be on Zoom until at least Tuesday, so.
Okay.
But yeah,
So-
I'm gonna have my regular office hours and I will have office hours next week on Monday and Wednesday at my regular times and also during my teaching times because I'm not teaching next week. So that'd be like 7 to 2 or something like that.
Okay, do you have time to answer a couple of quick homework questions now, or would you rather switch over to your Zoom link for office hours?
Oh, it's all the same. Anybody can show up here. So,
Okay.
yeah, so it's all good. So yes, I will answer your questions.
Okay.
Before that, can I just say, can I just ask real quick?
Yeah.
If it
3 for 3.
if it would be okay if I submitted the assignment, you said it might be okay a little like late tonight.
I got no problem with that.
Okay,
Yeah, that's a non-issue.
I mostly just gotta write some stuff up, so thank you. I might stick around and see what Jeff's wondering about, because I have one direction on one of the problems left, so if it happens to be that, I may hang about.
Yeah, the question I had is probably concerning what Jared was asking about, the backwards direction of 2D. So you gave me that approach for the forward direction, which I was able to make sense of and flush it all out, where I assume it's not one dimensional. And I use some other prime ideal to show that if we have X, it's actually a unit. And so it contradicts the almost integral, because it can't be an M, or M is the whole
So
value.
which direction of D are you doing? You're
So
starting,
I need to do the backwards direction now.
which
Assuming
I
it's
don't have it in front of me, so
dimensional.
tell me what that is.
Oh, sorry. So the problem is let V be a valuation domain that is not a field. Show that V is completely integrally closed if and only if V is a one-dimensional, if and only if V is one-dimensional. And so I have the forward direction. So now I need to do
You're
assume.
assuming
V-
it's one dimensional, you want to show that it's completely integrally closed?
correct.
Okay. So here's what you probably want to do.
Can I? Well, I guess I'll wait to see what you say. What you say first.
Well, so let me kind of draw a picture of this. So now you're in the situation where where it looks like this. So here's your valuation domain V. And it's one dimensional. So you have the maximal ideal M. And there are no primes inside properly inside of M except for 0, right?
Mm-hmm.
So, so let's think of it this way. So suppose that we have there we go. Suppose we have omega omega is in K non-zero and omega is almost integral over V, right? So there is a non-zero y in V such that y K is in V for all K. Correct?
Yeah.
So let me make a couple of observations. First, if omega is in K or in R or in V, we are done. So assume not. Okay so far?
Yep.
So we conclude that 1 over is in R. V, that is. 'Cause-
Valuation domain.
yeah, because it's a valuation domain.
Okay.
Now, and in fact, 1 over omega is in V, sure enough, but can you be more specific about where it is?
Yeah, it's got to be in our max ideal.
Because it's a non-unit and because it's quasi-local, so the maximal ideal has to be all the non-units.
Good. Is, okay, so that's better. And notice that since V is a valuation domain and M is only non-zero prime ideal, right? Because that's what it means to be one dimensional, right? M is the radical of any non-zero element of M.
This is what I was missing.
Right, because if you take a non-zero element, the radical of any ideal is the intersection of all prime ideals that contain it, right? Well, there's only one, right?
That's what I was, oh, dang it. I was trying to show it's radical so many ways and just looking at elements, but not thinking like the ideal theoretically about it.
Yeah, that's the power of the ideal theory, right? So are you okay with that, Jeff?
Can you say that again? You said that M is radical because it's the intersection of all ideals, or it's the, would you?
Well, no. So what I say is, if you take, I'm gonna change the color here. If you take a non-zero element of M, I'm gonna fail on my computer science students on general principles. Oh, I should probably stop recording then. There we go. Right, so if you have an element here that's not zero, right? Look at the ideal generated by X, right? That's a non-zero ideal.
Mhm.
look at its radical, right? Its radical is the intersection of all prime ideals that contain it. But there's only one, M.
Okay.